Last week you have gotten to know functions as essential building blocks of programs. This week we'll still be concerned with functions. We will get to know several ways to construct them and to compose them. Finally, next week we are going to look at data and objects. In the first session of this week we are going to look again at recursion, and we will find out that there are actually several ways to express recursion. First, let's review function application. You know from the last session that there's one simple rule. You evaluate a function application f applied to arguments e1 to en. By evaluating the arguments expressions e1 to en, they would result in the values v1 to vn, say, and then replacing the application of the function by its body, and at the same time replacing the formal parameters of the function by the actual arguments v1 to vn. This rewriting rule can be formalized by rewriting the program itself. Say you have a program with a function definition def f with parameters x1 to xn and a body b, and then somewhere else you have a function call f applied to argument values v1 to vn. That program can be rewritten to a program that contains the same function definition, but the function application has now been replaced by the body of f, b, and at the same time the formal parameters x1 to xn have been replaced by the argument values. And the rest of the program is assumed to be unchanged, which is assumed to be these triple dots here. That's areas of the programs that we do not touch. This notation v1 for x1, vn for xn is called a substitution. What we mean by it is that all occurrences in B of the values x1 to xn have been replaced by the corresponding values v1 to vn. Here's an example. Consider GCD, the function that computes the greatest common divisor of two numbers. We know an implementation for GCD since a very long time, since ancient Greek. It's known as Euclid's algorithm. To compute the greatest common divisor of two numbers a and b, what do? First, if b is 0, then a is a common divisor of both a and b. And otherwise, you compute the greatest common divisor of first b and then a modulo b. The percent sign here is, as in Java and C, means that a modulo b, the modulus of a and b. Let's try this algorithm in action. GCD 1421, how is that evaluated? Well, you would expand GCD, so that would give you if 21 equals 0, 14, else GCD 21 and 14 modulo 21. Then you simplify the condition, 21 equals 0 gives false. Next you simplify the if then else using the rule we have developed previously. So if false 14, else GCD of 21 and 14 modulo 21 would give the else part. Once we have the else part, we reduce its arguments to values. That gives us another call to GCD, which we expand, and the process repeats. I have signified that here with the multiple arrows to say these are reductions that take more than one step. You get GCD 14 to 7. You get GCD 7, 0, and finally you get the condition if 0 equals 0, 7, else some other call to GCD, and that finally, since the condition is true here, you get 7. Okay, let's look at another rewriting example, factorial. The classical algorithm for factorial is the following. You say to take the factorial of a number n. You ask again if n equals 0, then the factorial would be 1. Otherwise it would be n times factorial of n minus 1. Let's apply that algorithm to factorial of 4. So that would expand to the following conditional. If 4 equals 0, 1, else 4 times factorial 4 minus 1. You evaluate the if then else. That gives you in a couple of steps 4 times factorial of 3. Second part. Reducing further gives you 4 times 3 times factorial of 2. and so on, until you finally reach 4 times 3 times 2 times 1 times 1. That was the first case of factorial, and that reduces to 120. Question: what is the difference between these two sequences, GCD and factorial? Well, one important difference is that if we come back to GCD, we see that the reduction sequence essentially oscillates. It goes from one call to GCD to the next one here, to the next one here, to the next one here, and finally it terminates. In between we have expressions that are different from a simple call, like the if-then-else's, but we always come back to this shape of the call of GCD. If we look at factorial, on the other hand, we see that in each couple of steps we add one more element to our expressions. Our expressions becomes bigger and bigger until the end, when we finally reduce it to the final value. So that difference in the rewriting rules actually translates directly to a difference in the execution, in the actual execution on a computer. In fact, it turns out that if you have a recursive function that calls itself as its last action, then you can reuse the stack frame of that function. This is called tail recursion. And by applying that trick, it means that a tail recursive function can execute in constant stack space, so it's really just another formulation of an iterative process. You could say a tail recursive function is the functional form of a loop, and it executes just as efficiently as a loop. So if we go back to GCD, we see that in the else part, GCD calls itself as its last action. And that translated to a rewriting sequence that was essentially constant size, and that will, in the actual execution on a computer, translate into a tail recursive call that can execute in constant space. On the other hand, if you look at factorial again, then you see that after the call to factorial n-1, there was still work to be done. Namely, we had to multiply the result of that call with the number n. So that call here is not a tail recursive call, and it becomes evident in the reduction sequence, where you see that actually there's a build-up of intermediate results that we all have to keep until we can compute the final value. So that factorial would not be a tail recursive function. Both factorial and GCD only call itself, but in general, of course, a function could call other functions. So the generalization of tail recursion is that if the last action of a function consists of calling another function, maybe the same, maybe some other function, the stack frame could be reused for both functions. Such calls are called tail calls. After having gone through the exercise, you might ask yourself, should every function be tail recursive? Well, not really. The interest of tail recursion is mostly to avoid very deep recursive chains. Most implementations of the JVM, for instance, limit the maximal depth of recursion to a couple of thousand stack frames. So if your input data are such that these deep recursive chains could happen, then yes, it's a good idea to reformulate your function to be tail recursive, to run in constant stack frame, so as to avoid stack overflow exceptions. On the other hand, if your input data are not susceptible to deep recursive chains, then clarity trumps efficiency every time. So write your function the clearest way you can, which often is not tail recursive, and don't worry about the stack frames that are spent. As Donald Knuth has said, premature optimization is the source of all evil, and that's a motto that's very valuable to follow. Coming back to factorial, you might have observed that factorial grows really very, very quickly. So even after a very low number of recursive steps, it will already exceed the range of integers or even long integers. So in that case, definitely it was not worth making factorial a tail recursive function. So we did that only as an exercise so that you have the techniques ready when you need them. So let's do an exercise on tail recursion. You've seen factorial, and we've seen that that version of the function was not tail recursive. So now the task is to design a tail recursive version of the same function. Okay, so the most convenient way to solve this exercise is using another worksheet. I have already created a new package in our ProcFun project called Week 2, and in that package we have a worksheet exercise in which I've already written the signature of factorial, but I've left out the implementation. So how would we implement that in a tail recursive fashion? Actually, it turns out that we need another function, call it loop, that takes 2 parameters, not 1. I'll give you an outline of loop here. So the idea is it would take an accumulator that's also an int and the current value, and it would ask if the current value is 0, then it wouldn't return 1 as before but the accumulator, and otherwise it would return something else, and we would start the program with loop of an initial value of the accumulator and the current value of n. So the question is, what do we need to do to fill in the question marks here? The first task is to fill in something for the initial value of the accumulator. Here it's pretty clear that we say, well, if n equals 0, then the accumulator is returned, so it has to be the right value for n equals 0, and that would be 1. So we pass 1 here. The second question is, what do we do in the case where n is not equal to 0? And the idea there is we would go again into the loop with the accumulator times n, the current value, and n reduced by 1. And that thing still doesn't compile because we have forgotten to give a result type to loop. Once we do that, factorial compiles, and we can test it. So let's do that. So that would give 24 as expected. In this session we've gotten to know tail recursion as a special case of recursion that corresponds to a loop in an imperative program. In the next session we are going to cover new ways to compose functions.